Hey everybody, Mr. Tannen here. Hope everybody had a nice weekend. Check me out, I got some of these blue light glasses. I just thought I'd make a quick video. Thanks. I saw a bunch of people already signed up. I'm gonna take a gander here at number 48. This is one of these funky parametrization, however you want to pronounce it. It's up to you. The first part of the question is asking us to graph the curve. So for this case, you could you could identify the initial and terminal points, if any, indicate the direction in which the curve is traced. Well, if we look at number 48, which was one of the ones assigned here, well, if you notice, we only have an upper bound on t. So since there's no lower bound on t, um, basically we're going to end up, there's no initial point, I guess we could say, because x, there's no lower bound, I should say. But if we look at the graph here, what we could do is we could just try plugging in t at 2 to see the upper bound. And if we do that, well, we would get x would be 3, because 1 plus 2. And in that case, y would be the square root of 4 minus 2 times 2, or 0. So we have the point 30. So that's all really a parametrization of a curve is where we have, like I mentioned very briefly in class, two separate functions for both variables. So in this case, we know that we are going to have the point, let me go by 2 here. I know it's not a perfect graph. It looks like we get the point 30 as what we will call the terminal point. So that was the first part of our graphing situation, or first part. So we would say something's being, I think it's being very laggy. Maybe it's because I'm recording. So we could say the terminal point is 30, no initial point. And because there's no initial point, no lower bound, we would graph the point, graph it in this direction where we're going from left to right. And you could see this if you were to graph this using your calculator. I could show quickly how you can graph parametrized curves using your graphing calculator. One way to do this is if you go on your TI grapher, if you notice when you scroll down, in this case it's my 5th row, but there's actually a parametric option. And then when I go here, I could simply put in the equation as I had it. What was it again? 1 plus t and you notice now if I hit the xt theta button there, instead of putting an x, it automatically puts a t because I'm in the parametric mode. And then I could do my square root of 4 minus 2t second square root. Sorry if I'm making this video more boring by going through this, but and then if I go to hit graph, you can see graphs are just like that. I wonder why it got cut off. Oh, maybe it just started at a certain value, because I think it could have more negative inputs. Let me check this out. Oh, that doesn't. I don't know why it had a T minimum in this case. Let me hit zoom as standard. I guess often in physics that's probably because you don't really consider negative time, but they didn't necessarily give us much context to this problem, so I think when we graph it, we could just sort of graph it in this manner, and it's going to end up hitting, it looked like, between 2 and 3, all the way to the terminal points. Oh, that's a really poor graph. Let me redo it, because it had some more like curve at the end like this. Still not great, but my thing is being a little funky. Well, the only thing I think that's misleading about that arrow is that even though it does go on forever, the direction is this way. And sometimes with parametrics, you'll do the direction. And basically, like, we know it's going in this direction because for the most part, the orientation of a parameterized curve is the direction, like, is determined as the parameter increases. So since we know this is the last point, like, we know it's going this way as t increases, because like basically parametrics, we're thinking more about like concrete scenarios with physics, like as time is increasing, where is this, and that's why we use t anyhow. So, and when you graph it on your grapher, it should also show you, as if it goes left from right, that's showing you the direction as well, with regard to indicating the direction in which the curve is traced. Alright, so this next part is actually, may sound intimidating, finding a Cartesian equation for a curve that contains the parametrized curve. But all it's really saying is, like, can you figure out what the normal function that models that graph would be? So basically, instead of being in parametric form, what would just be like the xy form of that? So there's actually a lot of different ways that you can approach this, and I know we looked at the answers online, and the way they had answered it was actually different from the way that I had chosen to do it. Because what I chose to do was, I noticed that in my or in the way they gave us the problem here, x equals 1 plus t. Well, it's quite easy to solve for t in terms of x. All I had to do is subtract 1 from both sides. So t actually equals x minus 1. So I could take this value, and since we know what t equals, I could plug it in here for t, and then I would replace my t's with x's, and I could simply figure out what the curve that modeled this parametrized curve would be. So I end up with 4 minus 2x, and then this actually becomes a plus 2 because I gotta distribute that negative. Let me just show this with different colors, right? So this becomes the square root of 6. Man, that thing is really being funky. This y would be the square root of 6 minus 2x. So if I went to my grapher now, let's go back to that same grapher, and let's just clear all this and go back to function mode. If I hit mode, which is the mode that we're most used to functioning in. I think it was y equals the square root of 6 minus 2, and now you see when I hit x, it just puts an x in there. Now when I hit graph, you can see it's the exact same graph with that terminal point at 3. And I don't think I guess I could specify that the graph would be traced for, all real numbers, like from an element of negative infinity to positive infinity, because it does stop at that same spot that the parameterized curve did. So anyhow, that's how we were able to get this. I know that the answer key had a different process, but I thought this process worked quite well. All we had to do was get t by itself and substitute x in, and we could say this is for all. Wow, this is really bumpy. I remember when we're talking about infinity, we use the parentheses for this um, interval notation because it's never actually going to include infinity because infinity is just a concept that it's approaching. So that was number 45, or sorry, 48. We've got the terminal point. There was no initial point. I guess I didn't say explicitly it's left to right is how we would graph it. And like I said, sometimes you would draw these little arrows to show that's the direction in which the curve would be traced. And then the Cartesian equation, we saw that actually has the same terminal point, so it would be exactly the same graph, so we could just say it's for x is the element of all real numbers. And it would be this y, this radical function here. So, and you can see like 3 would be the terminal point because that would give us the square root of 0. It can't take a square root of a negative, so 3 is as big as x could be, just like it was in our parametrized curve. Alright, I'm going to stop myself here before I drag on too long. Hope for people who had questions that this was helpful, and if it wasn't, let me know. Have a nice day, everybody.